Welcome back to the deep dive. Today we are strapping on the loops and plunging directly into the mechanical reality of joint replacement, specifically total knee arthroplasty.
Mm-hmm.
We're not talking about the beautiful post-op x-rays here. This is about the hidden microscopic grind that, determines if a component lasts 5 years or 25.
It's really the moment of truth. For those of us who spend any time in the retrieval lab, the orthopedic morgue, if you will, this is where you get the unvarnished facts.
Right.
It's where the rubber meets the road, or I guess more accurately, where the ultra-high molecular weight polyethylene meets the cobalt chromium. We're going deep into the material science of why these things fail.
So our mission today is really a forensic one. We're using retrieved real-world components to figure out the unavoidable phenomenon of wear. We're asking, why does the poly fail? What are the mechanisms? What does that interaction actually look like when it leads to a revision?
It's fundamental. And I think it's sometimes forgotten that wear is just it's the inevitable outcome. You can't move two materials against each other under load without generating some kind of debris. You just can't.
So the whole game is just controlling it then?
The clinical focus shifts entirely to controlling that debris. Absolutely. The questions become, okay, how much debris is being produced? What size are the particles?
And critically, how much material loss is too much, right?
Exactly. What volume loss starts to affect the macroscopic mechanics? When does it cause instability or loosening? Because that's what dictates the patient's biological response, the osteolysis, and the ultimate stability of the device.
As we were digging into the literature for this, 3 big observations just kept coming up. I started calling it the resident's pre-op brief for the retrieval lab, sort of the 3 things you need to know before you even look at the component.
Okay.
First, that wear and damage are totally distinct phenomena in knees.
Crucial. We have to stop using those terms interchangeably. Wear is volume loss. Damage is, well, it's just cosmetic.
Second, and this is where the engineers I talk to always sigh, is that measuring true wear in knees is just so much harder than in hips. The metrology is a nightmare.
A complete nightmare. We'll definitely get into that.
And third, which I found really surprising, is that the design and the system you choose can be just as influential as the materials themselves.
Oh, absolutely. The best polyethylene in the world can be completely sabotaged by a poor tray locking mechanism or the wrong geometry. It happens all the time.
Precisely. So we're going to get technical today because precision really, really matters when you're talking about changes at the micron level that can send a patient back to the OR. So let's jump into the pathology report.
Let's start with that first point because it's so important. The dichotomy between damage and wear.
Okay.
When a surgeon sends an implant to a retrieval lab and the form says polyethylene wear, so often they're confusing what they see, which is highly visible damage, with actual volumetric material loss.
It's the difference between a scratched bumper and a blown engine, right? One looks awful, but the car runs fine. The other is catastrophic.
That analogy is perfect. Wear is the measured, quantified loss of bulk material. It happens through abrasion, adhesion, or fatigue. If you have wear, you have volume loss, and you have debris.
Okay.
Damage, on the other hand, is just those superficial surface changes. Scratching, pitting, the things that look terrible in the photos, like in figure 24.1. But it often represents almost no material loss.
So the scratching is like a scuff mark on the car's paint. It tells a story, maybe about a bone fragment that got trapped in there, but the actual integrity of the component is fine.
Exactly. Whereas true fatigue failure, that's like hitting a pothole so hard the axle breaks, you get these large macroscopic chunks of material just gone.
A catastrophic failure.
That's a great way to put it.
Yeah.
And if we focus on that cosmetic damage first, you see it on almost every single clinical retrieval. Figure 24.1 shows it across all the different generations of poly.
And we know the source is third body debris, bits of cement, bone chips, maybe some porous coating beads that have come loose.
Right.
But here's where the tribology gets really interesting for me. Why do we sometimes see scratches, not just on the poly, but on the cobalt chromium itself?
Ah, that's a critical insight. It comes from studies like the one by Atwood. What happens is that a hard particle like bone cement can get embedded into the softer polyethylene.
So the poly becomes the tool holder.
It becomes the tool holder, exactly. It acts like a tiny persistent little burr. And so when that happens, you have this hard particle trapped, and it can actually scratch the much harder metal counterface.
Wait, I always thought of the metal as basically impervious. You're saying a soft plastic bearing with a tiny piece of cement stuck in it can scratch a hard metal alloy?
It sounds totally counterintuitive, I know, but it's a well-documented thing in tribology.
Yeah.
The hardness of that embedded particle matters way more than the hardness of the matrix it's sitting in.
Wow.
And once that metal surface is scratched, you've immediately increased the roughness. And more roughness means more friction, which then dramatically accelerates the wear on the polyethylene itself.
So the initial scratch is superficial damage, but the long-term consequence of the debris that caused it is an acceleration of true wear.
Now you've got it. And that sets the stage perfectly for the really catastrophic failure mode we mentioned. Fatigue failure.
Yeah.
The material's slow betrayal over time. If you look at figure 24.2, you see that cracking and delamination. Historically, that was the main way these TKAs failed.
Right, before we got better at sterilization.
Before the widespread adoption of modern gamma barrier sterilization, yes, this failure is all about time, cycles, and oxidation. Oxidation, especially in the old components sterilized in air, just made the material brittle. It reduces ductility, its fracture toughness. So as the cycles pile up in the body, microcracks start to form.
And the mechanism here isn't random. It's driven by a really specific mechanical coincidence, isn't it?
It is. It's a crucial point. In these non-conforming knee designs, the maximum contact stress isn't right at the surface. It's actually subsurface. It's dictated by what we call Hertzian contact mechanics.
Okay.
At the same time, oxidation is a diffusion-limited process. So oxygen also penetrates and builds up just below the surface.
So you get this perfect storm. You have the collocation of maximum subsurface oxidation and maximum contact stress, usually at about 1 millimeter deep.
Correct. That 1 millimeter depth becomes the crack nucleation zone. The stress allows the cracks to form. The now brittle oxidized material can't stop them from propagating, and they start to run parallel to the surface like a fault line.
And then they turn up.
And then they turn up, leading to these huge spalls or delaminations. We're talking millimeter-sized chunks of material just gone. A bulk catastrophic removal that completely compromises the bearing.
And this brings us to the really important biological distinction about debris size.
This is key to understanding osteolysis. The debris from fatigue failure is huge, millimeter size. It's generally considered not very biologically active. It doesn't really trigger that chronic inflammatory response.
It's a mechanical problem, not a biological one.
Mostly. The real stealth bomber, the particle that's historically associated with severe osteolysis, is the fine stuff. The submicrometer-sized debris that comes from adhesive and abrasive wear mechanisms.
So abrasive wear is the slow, chronic threat. That's the stealth bomber silently triggering the macrophages.
Yes.
And fatigue wear is like a B-52 dropping these huge chunks that cause immediate mechanical instability, but maybe don't trigger that same systemic response.
That is a perfect way to describe it. In hips, where that adhesive and abrasive wear dominates, we know that wear rates as low as 0.1 millimeters per year are enough to cause clinically significant osteolysis.
Right.
So the focus in knee research today is hunting for that finer particulate debris, especially now that we've largely mitigated the catastrophic oxidation and fatigue problem.
So if the fine debris is the enemy, and we know where is happening, the next step is obviously to quantify it. But as you said at the top, that's where the fun stops and the measurement nightmare begins.
Yeah, that's putting it mildly.
Okay, so we're moving into metrology. As a resident trying to document a retrieval, why is quantifying TKA wear so difficult? Why does the knee defeat our best attempts when the hip is, comparatively easy?
It's all about the geometry. The
Mhm.
hip is just, it's beautifully simple. A ball in a socket, a hemisphere.
So it has a built-in reference frame?
It has an intrinsic, reliable reference frame. You can measure the radius, the curvature. You can establish a datum surface based on that sphere. It's predictable.
But the knee is this chaotic mess of complex curves.
Exactly. Knees have non-conforming surfaces. You've got complex sweeps, multi-radii, blends, all designed to allow for translation and rotation. You lack those good, reliable, built-in reference points to measure from.
So how do labs even try to get around that?
Well, it's why retrieval scientists often argue that manufacturers should be required to embed, non-functional fiducial marks or reference wires deep inside the poly.
To create a known location.
To create known locations for precise measurement relative to the original CAD file. But that's often not done. And the problem is made even worse by all the deformation we just talked about. Plastic creep, warping, which can sometimes be even larger than the dimensional changes from true material loss.
Right.
And that's where you hit this fundamental ambiguity. It's illustrated so well in figure 24.7. You look at the backside of an insert, and you see these little pegs or extrusions of poly poking out of screw holes.
So you're faced with two totally opposite interpretations.
Two completely opposing stories. Interpretation A. These pegs are just cold flow. Plastic creep. Unsupported poly, they got pushed into a void under load. That's deformation, it's damage, but it's not material loss.
Okay, benign.
Right. Versus interpretation B. These pegs are actually plateaus of unworn polyethylene. They represent the original material height, and all the material around them has been worn away.
Which is a huge deal. That implies significant material loss and debris.
A massive amount. So
Yeah.
if it's A, it's benign deformation. If it's B, it's clinically significant wear. And telling the difference is, well, it's extremely challenging.
So how do you even try?
You have to use really sophisticated metrology, coordinate measuring machines, or CMMs, or specialized digitization of the surface. You compare the retrieved component, point by point, to the manufacturer's original CAD model.
I see.
If the peg height matches the CAD thickness perfectly, that's strong evidence for interpretation B, the wear plateau. If the peg height is taller than the CAD thickness, it suggests cold flow. But even then, it's still hard because of manufacturing tolerances and warping.
This just perfectly explains why the literature stresses that just looking at it, the visual damage rating is such a poor predictor of actual material loss.
It's a critical lesson for any surgeon. The look of an insert means almost nothing for true volume loss. Let's look at figure 24.6. It's such a vivid contrast. You've got this highly scratched LCS rotating platform insert. It was in for nearly 13 years. It looks terrible. Cosmetically, it's a disaster.
But its measured backside wear volume was only 267 cubic millimeters.
Now compare that to the PFC fixed bearing insert in the same figure. It was in for almost 12 years. It looks relatively smooth, much less cosmetic damage.
But its backside wear was a staggering 1742 cubic millimeters.
Almost 7 times the material loss. Even though it looked better visually, it just hammers home the point that you have to quantify the volume of material removed. That's the real determinant of the risk.
So if visual inspection is out, what quantitative numbers can we actually rely on? If we look at the big retrieval series, like in table 24.1, what are the takeaways?
There is some convergence. The average linear depth penetration rate, it tends to narrow down to a pretty predictable range. You're looking at about 0.04 to 0.07 millimeters per year across the big series for modern fixed bearings.
Okay, so that's a number we can hang our hats on.
It's the most reliable figure we have. It's also really important to note the universal finding of the bedding in effect.
Right, where the wear rates are always higher for short implantation times.
Consistently. And this reflects a few things. Part of it is the joint just finding its kinematic groove, as you'd expect.
But there's more to it.
There is. It also reflects the initial surface roughness smoothing out. But a big part of it is probably third-body contamination from surgery. Debris causes rapid wear in that first year, but then those particles migrate out of the joint, and you settle into that lower steady-state wear rate later on.
And where is that wear focused in fixed bearings? What's the bias?
Fixed bearings tend to show more wear posteriorly, which makes sense from deep flexion, and crucially, medially.
Which aligns with the native knee's kinematics.
It does. The medial compartment in a natural knee sees greater loading and has less rotational freedom.
Right.
So the wear patterns are kind of respecting the native biomechanics.
This quantitative data, showing us where the loss is happening, it leads us right out of pure material science and straight into the mechanical engineering of the device itself.
And this is the section that really emphasizes that what we do, orthopedic surgery, is applied mechanical engineering. You can have the best polymer in the world, but if the device geometry encourages failure, it's going to fail.
So let's start with the biggest misnomer out there, the so-called fixed bearing. If you look at figure 24.5, it's so clear that modular fixed bearing knees are absolutely not fixed. You see clear evidence of micromotion between the poly insert and the metal tibial tray.
The micromotion we see is almost all rotational. And the engine for that rotation, it's the torque being transmitted directly from the femoral component during loaded flexion.
So every time a patient stands up from a chair or climbs stairs,
the femoral condyle is trying to rotationally drive that tibial insert. Figure 24.12 shows that concept really well.
And the locking mechanisms, the little peripheral rims or the central posts, they're not strong enough to resist that torque over millions and millions of cycles.
They're completely inadequate. And the consequence is devastating. As the backside starts to wear, the abrasion loosens the fit. And this creates a destructive positive feedback loop.
More motion, more wear.
More motion leads to more wear, which creates a looser fit, which then allows even more motion. Just gets worse and worse. And we see those rotational wear marks so clearly in the retrievals.
Which brings us to conformity. This is the classic orthopedic designer's dilemma, isn't it?
It's the trade-off, absolutely.
Yeah.
We want high conformity, a nice, deep, congruent poly surface, because that reduces the contact stress on the top, on the articular surface. It prevents fatigue failure.
But that perfect fit has a dark side.
It creates a better clutch. The articular geometry directly determines how efficiently torque gets transmitted to the backside.
And the data on this is pretty clear.
Oh, very clear. Studies showed that the more conforming curved inserts have significantly more backside wear compared to the flatter, less conforming designs. The comparison in figure 24.8 makes it really obvious. A flatter surface allows for a little bit of slippage, which dissipates some of that rotational energy.
So the counterintuitive lesson is that a highly congruent design, which solves the topside fatigue problem, acts like a more aggressive clutch and just transfers all that rotational force to the insert tray interface, chewing up the backside instead.
You're trading one failure mode for another. You solve the catastrophic problem of the poly falling apart on top, only to uncover this hidden, chronic, debris-generating problem underneath. The design dictates where the failure will occur.
This makes me think about the role of cement. Is this a biomechanics problem or a surgical technique problem? Because it seems like cement plays a much bigger role than we thought.
It is huge. There was a crucial retrieval study that compared PFC fixed-bearing knees. They controlled for the geometry, so the only big variable was fixation.
And what did they find?
A staggering difference. The cementless group had a significantly lower wear rate than the cemented group.
And you can see it right there in figure 24.11. The linear backside wear depth is so much lower in the porous-coated group. What's the mechanism?
It's third-body sabotage. Cement debris is a persistent abrasive. During surgery, extra cement gets squeezed out, it hardens, it fragments, and those little fragments act like sandpaper floating around in the joint.
So as the insert rotates with that micromotion,
It grinds those cement particles against the backside of the poly in the metal tray. This persistent abrasion is what causes those rapid rotational wear patterns you see in figures 24.12 and 24.13. So cementless fixation, just by getting rid of that primary source of abrasive particles, showed a huge reduction in backside wear.
so if we can't completely get rid of micromotion and we know debris is going to be there, the next logical step for designers was to make the tibial tray surface as friendly as possible.
Right. Historically, the trays were often made of titanium alloy and were intentionally left rough or grit blasted.
To help the cement stick.
Exactly. But retrievals from those rough trays show these unmistakable stippling marks and arc marks on the poly. You can see it in figure 24.14. The stippling is exactly where debris particles got trapped and caused localized wear.
Creating more debris, which then causes more wear.
The cascading failure mode. So the move to a polished metal tray surface, usually cobalt chromium, was aimed right at this problem. And the data is so compelling. A study by Barry showed polished trays cut the backside wear rate down to 0.006 millimeters per year, compared to 0.02 for the rough titanium trays.
That's a nearly 70% reduction just by polishing the surface.
It's a phenomenal improvement. And crucially, the long-term data backs it up. You can see in figure 24.16 that the low wear rate of polished trays stayed low out to 6 years. The rough titanium trays, on the other hand, showed an increasing wear rate over time.
That positive feedback loop again?
Exactly. Now, even polished trays can show some stippling, as you see in figure 24.15, especially if they're cemented. It all points back to the pernicious role of that cement debris.
Let's shift gears to posterior stabilized knees. Here, the design relies on that little posting cam mechanism for stability. The intent is pretty clear, right? Contact should be on the posterior side of the post during flexion.
That's the design. The retrieval reality, however, tells a very different story. A story of, well, misuse.
What do the studies show?
Studies by Pulaski and Currier show frequent and really significant damage on the anterior and lateral aspects of the posts. Figure 24.9 illustrates it well. Deformation of the anterior corners happened in something like 86% of the retrievals they analyzed.
That level of damage means the knee is being pushed into zones the post was never designed to handle.
Precisely. It suggests two main problems. First, the knees are going into hyperextension, hitting the post anteriorly like a hard stop. Second, there's excessive internal or external rotation, causing that lateral impingement.
And you can tell which is which by looking at the wear pattern.
You can. Uniform impingement right across the front suggests a simple hyperextension. But that characteristic bow tie pattern on the anterior surface, which you can see in figure 24.9, that is the fingerprint of rotational impingement.
And these forces aren't just cosmetic, they're actually deforming the implant.
Oh, absolutely. The torsional forces can be immense. They can lead to permanent structural changes, what we call torsional deformation.
Which you can see in figure 24.10.
Yes. It's not uncommon to find a permanent twist of 10 degrees or more in that polyethylene post. It's just a harsh reminder that alignment and soft tissue balance, the surgeon's part of the equation, are absolutely critical to making sure that post and cam works as intended.
Okay, so we've really picked apart the fixed bearing systems.
Mm-hmm.
Let's look at two of the big attempts to solve these problems. Mobile bearings and, of course, highly cross-linked polyethylene.
The next frontiers.
Let's start with mobile bearings, like the LCS rotating platform or unicondylar knees.
These were designed to tackle two of the big fixed bearing problems, tibial tray loosening and issues from rotational malalignment. And they really deliver. Retrieval studies confirm they do much better against loosening.
Right.
And they offer that benefit of self-alignment, which can potentially reduce damage to the patella.
But you inherently introduce a second articulating surface. The backside is now a bearing, so theoretically you should be generating more debris overall.
That's the classic trade-off. It's a dual articulation system. And yet, the overall wear profile is surprisingly good. The wear rates are generally quite low. For example, the Signa RPs averaged only 0.027 millimeters per year, which is, at the low end of what we see in fixed bearings.
So why do they perform so well, even with double the articulating surfaces?
The key is the motion pattern on that backside. When you look at retrieved mobile bearings, you see evidence of almost exclusively unidirectional rotational motion. You can see it in figure 24.21. It's clean. It's not the messy, multi-directional micromotion you see in fixed bearings.
And from a tribology standpoint, unidirectional motion is much less damaging than cross-shear, right?
Much less. Unidirectional sliding against a polished cobalt chromium tray is a very, very favorable environment. It's what contributes to those low wear rates despite the huge articulation area.
But interestingly, mobile bearings show that bedding in period, that high initial wear, much more strongly than fixed bearings. You can see it in figures 24.17 and 24.18.
That initial spike is really significant. It suggests a really strong link to third body contamination because the bearing is always moving. Any debris from surgery cement, bone gets spread across that huge surface area very quickly.
So you get high initial wear until those particles get cleared out.
Exactly. And this is why, as you see in figure 24.18, a mobile bearing surface can show really severe surface damage after only a few months. It can look just as bad as a long-term fixed bearing, even though the quantitative wear is actually very low.
Which brings us to highly cross-linked polyethylene, HXL. This was hailed as the miracle material after it was so successful in hips.
It virtually eliminated abrasive wear in hips. The rationale for using it in the knee was a bit different, though. It was mainly to get rid of oxidation and that subsequent long-term fatigue failure that plagued the older inserts.
And the simulator studies looked great.
They all look great. They consistently showed improved wear performance. But clinical retrieval data, the ultimate test, has introduced what I call the HXL paradox in the knee.
You're talking about the big comparison study by Courier. What was the finding there?
They found no statistically significant difference in the wear rate between HXL and the conventional gamma N2 sterilized materials, even out to 9 years. You can see the data in figure 24.22. It really challenges the simulator data.
Why do you think the simulators got it so wrong?
Simulators They struggle to replicate the complex, non-conforming, multi-axial kinematics of a real knee, especially torque. In the knee, it's the mechanical failure modes, fatigue, deformation, torque-driven backside wear that really dominate. And HXL, while it's chemically superior, might not give us the mechanical advantage we hope for in this specific joint.
And the paradox gets even deeper when you look at what's happening to the material inside the body.
This is the concerning long-term data that every surgeon needs to be watching. There are two really unexpected findings. First, HXL materials do oxidize in vivo, and they do it at a rate that's surprisingly indistinguishable from the conventional gamma barrier material.
You can see that on the left side of figure 24.23.
Yes, the oxygen is getting in. And second, and this is the real ticking time bomb, is that HXL material oxidizes in the body. Its cross-link density, the very property that gives it its wear resistance, it starts to decrease.
That's the right side of figure 24.23. The cross-link density is going down over time.
It's going down. It's tied directly to oxidation. It suggests the material is slowly reverting. The whole point of cross-linking is to create these strong bonds. If those bonds are degrading over time, we're fundamentally losing the properties we paid for. We may have only delayed the fatigue failure clock, not eliminated it.
So what about the cosmetic look of HXL? The retrievals often show a lot of plastic deformation and pitting, like in figure 24.24. They can look just as rough as the old stuff.
And this is where we have to come back to that wear versus damage distinction. A lot of that deformation you see on HXL surfaces is actually recoverable. The material has an inherent shape memory property. You see it demonstrated in figure 24.25.
So the surface looks deeply indented, but the material isn't actually gone. It's just temporarily deformed and might spring back.
Exactly. It's damage, not permanent wear. And that's a benefit, in a way. It shows HXL can absorb high-stress contacts without permanent volume loss. But it means we have to be so critical of visual inspection. The surface can look terrible, but the actual quantified wear is still minimal.
This has been an incredibly detailed look into the forensic pathology of TKA failure. It really emphasizes that when we put in a joint replacement, we're starting a multi-decade tribology experiment. Let's try to summarize the key lessons to take back to the OR and the clinic.
Okay. First, the fundamental distinction. Don't confuse damage with wear. The cosmetic scratching and pitting is not the same as actual volumetric material loss that generates particles and causes osteolysis. Appearances are always deceiving.
Second, the quantification challenge. It's difficult to measure, but the data is clear. Fixed bearings are not fixed. Backside wear is a huge contributor to the total debris load, and it happens at a pretty predictable rate of 0.04 to 0.07 millimeters per year.
Third, and maybe most important, wear is a systems issue, not just a material issue. The design drivers, high conformity transmitting too much torque, or surgical inputs like cement and alignment are massive determinants of the outcome.
We can mitigate a lot of that, though.
We can.
Yeah.
You can mitigate backside wear by choosing a polished tray and being meticulous with your cement. You can reduce post-impingement by getting your alignment and soft tissue balance just right.
And of course, we have to remember the big caveat of all retrieval studies.
It's vital. These samples are inherently biased toward failed devices. We're looking at the failures. We can identify phenomena like the bow tie pattern or the decreasing cross-link density in HXL, but we can't extrapolate the incidence rate across all the successful implants out there. Retrieval studies tell us how things fail, not how often.
So given everything we've learned, that the ultimate test is the patient, in vivo, and these concerning findings about HXL oxidizing and losing its cross-link density over time, what's the most provocative question we should be asking about the future of TKA?
We have to be prepared for delayed failure. The early clinical results for HXL are excellent on wear, but the material science is sending a clear signal. The very property that gives it that resistance is degrading over time inside the patient.
So what does that mean for 15, 20 years from now?
That's the million-dollar question. What long-term mechanical failure modes are we setting the stage for? Will we see a resurgence of late-stage fatigue failure when that HXL material functionally reverts to something closer to conventional poly? Will we see a sudden spike in abrasive wear? This material degradation is a molecular ticking clock, and that's exactly why retrieval studies have to remain a core part of what we do. They force us to ask the hard questions that a benchtop simulator never will.
A truly successful arthroplasty is one that defeats the inevitable. Thank you for guiding us through this ultra-high molecular weight conversation.
My pleasure. Stay sharp and always inspect your retrievals closely.